Right, so in this video we're going to prove Stewart's theorem. So that's Stewart's theorem, and we're going to show, we're going to prove it by means of what we already know. That is, if a point divides a line in the ratio, in a particular ratio, then we know the coordinates given the coordinates of the extreme points of the line segment. So with all those in mind, let us first define what Stewart's theorem is. And let me just change my color to an orangey one. Yep, this is good. Right. So Stewart's theorem says that if we have a triangle ABCD and we have a angle, well, not a bisector, but line which passes through A, such that it intersects this angle and intersects the line BC at a particular point D, then Stewart's theorem says that AC square times BD plus AB square times DC equals BC times AD square plus BD times DC. Now it's a messy looking formula because you can imagine that this is very generally applicable. We haven't really put any condition that it should bisect this line BC in a particular ratio, or the fact that the triangle needs to be isosceles or equilateral or anything of that sort. We have no foundations. So we ought to get a very messy looking formula, in which we do. Now the thing is, to prove this, we can assume that, say, D divides the line BC in a particular ratio m to n. Now m and n can be anything at this point. We really haven't added any restriction to our system. It is as general as possible. M and n can take any values. We prove it for all m and n. And with that in mind, let us define the coordinates of point A. Let's call that x sub A, y sub A. Point C is lying on the x-axis, so that makes it its x-coordinate, say xc, and the y-coordinate will be 0. B lies on the origin. This is what we have chosen. So we can call B to be the origin in the sense that the coordinates are now 0, 0. Now, if D is dividing the line segment BC in the ratio m is to n, then we know the coordinates of D. And by the formula that we have already used, that is m times xc divided by the sum of the ratios, comma, do the same thing with the y-coordinate of xc, but remember the y-coordinate of x is 0, and so is the y-coordinate of B. What that means is we get 0 here, and that makes sense because if you're dividing a line segment that clearly lies only on the x-axis, every point on that, even that particular point that divides it in the ratio m is to n, should lie on the x-axis and should not have any y component. So that makes sense. So we have BD, we have BA, we can find AC, we have all those things. We just need to substitute it there and check whether this statement holds this statement. Alright, so let's write the LHS, or the left-hand side of the equation, which is AC square times BD plus AB square times DC, right? So AC square is this, right? So that would be a minus xa minus xc whole square plus ya square times BD, which is this. That is mxc upon m plus n. And we add that to BC, AB square times DC. So AB square is this segment's square, and that is just xa square plus ya square, because b is 0, 0, 0, and we multiply this by the term dc. Well, dc is xc minus this term, and if you work the maths out, that just becomes n times xc rather than m times xc divided by m plus n, and that is our left-hand side of the equation. What about the right-hand side of the equation? Well, let me write that in red. So the right-hand side of the equation follows as so. BC, which is this whole length, that is just c, x sub c, multiplied by AD square. Now AD square can be calculated because we know the points A and point D, we know the coordinates, so that's xa minus xc times m by m plus n whole square plus ya minus 0 square plus, now bd times dc. Well, bd is just this and dc is just this, both have the same form, and we have already calculated dc here, which is this term, and bd is this term, so we just multiply them out. That makes xc squared because that comes 2 times m times n, and from here and from there, divided by m plus n whole square, because we have that twice as well. Now, let us look at what cancels out, because we want to show that RHS equals LHS. We need to show that LHS equals RHS, right? So if we have similar terms occurring on both sides, we can simply get rid of them and try to prove whatever remains. I notice a ya square quite simply present here, and on the LHS we have a ya square multiplied by this fraction times a ya squared multiplied by that fraction, and if we really think about it, if we add m times xc to n times xc, we get m plus n times xc, and when we divide that by m plus n, we simply get xc, which is clearly just the term here, because this gives us xc times y squared, and when we add these two terms out, we should get xc times y squared as well. So that cancels out this particular term. Let me do that right now. So ya squared cancels out from the entire equation. We're left with just xa and x sub c. That's workable now. So we notice that we have xa minus xc whole square, m times x. Let me write that down in this case. Xa minus xc whole square times mxc by m plus n plus xa whole square nx sub c upon m plus n equals, well, this should equal to, I'm putting an equality here, even though I'm not very sure of it, because at this point we're just proving it, but never mind that, xc times, okay, then that's kind of nasty, xa minus xc by m plus n whole square plus xc square mn upon m plus n whole square. Okay, now let us look at the xa squared term. So we get an xa square from here, and we also get an xa square from here. So that gives us xa square times mxc from this coefficient, and we get an nxc from there, plus, well, xc square times mxc upon m plus n minus 2xaxc from this times mxc upon m plus n. Well, this should equal to whatever we had there. Okay, I'm just I'm not writing it down here, but I'm not really simplifying that. From here, we notice that this is again the same form, which helped us cancel out the y sub a terms, because this is m times xc and n times xc. When we add them up, we get m plus n times xc, so that basically cancels out, and we are left with just the term xc from here. So we get xa squared times xc as one of the terms. So I can erase this right now and just write xa squared xc. So let us try to cancel out this term if we can find it on the right hand side. Well, the right hand side also has an xa squared term here, which very conveniently multiplies by the coefficient on the outside of the entire bracket, so that cancels that out, and we have taken care of that. Let me change my pen again. Ooh, yeah, this works. So xa gets cancelled out here, and that also cancels this out and this out, right? So we don't really need this term now. We're left with this, this, and we need to equate that to, we're left with this and this, and we need to equate that to whatever remains here. Okay, it's getting a bit better now. Well, let us write that down a bit clearly. X sub c square upon mxc upon, multiplied by mxc upon m plus n right there, which is this term. Then we subtract 2xa xc m, well, xc again, by m plus n, and that should be equal to, let us expand this out. So the first term is this term. Let us write that down quickly. That is xc whole cube, because you have an xc square here and xc outside, so that gives you an xc whole cube times mn upon m plus n. Well, that's an m plus n whole square. Okay, so we have taken care of this term. Let us expand this term without the xa squared term and multiply an xc to that. So the first term would be xc squared m squared upon m plus n whole squared multiplied by an xc outside, so that makes it an xc cube, and that's m squared upon m plus n whole square, right? And the last term would be minus 2xa xc, but we have xc outside as well, so that makes it an xc square times m divided by m plus n. Let us look at something that gets cancelled out. But we have an xc squared here, and we have an xc squared here, and we also have a minus 2xa, and we have the same ratio, m upon m plus n. That basically cancels this term out. What about the remaining terms? Well, let us look at that. So we have xc cube on both sides, and we have m upon m plus n here, and here we have xc cube. Let us take that out as common, divided by m plus n whole squared, and let's write the whatever remains, that is mn plus m squared. If we take m common out of this, right here, we divide this by an m, we divide this by an m, we get n plus m. So that reduces down to n plus m, and that very conveniently cancels out the denominator, at least one power of it, and what we're left with is xc whole cube m upon m plus n equals xc whole cube m upon m plus n, and that's an identity. That's an identity. So it holds for any ratio of m and n and any value of xc, and what actually got cancelled out as well. So we really don't need to have any restrictions on it, and as I already showed you, even though we are choosing this to be in a particular ratio, m is to m, we actually showed that this is valid, this result is valid. Stewart's theorem is valid for any ratio m is to m, so it really doesn't matter. So by this whole lengthy description and this whole lengthy derivation rather, we were able to prove Stewart's theorem right there. So all we needed was the formula that helped us write the coordinates of the point D, which was dividing the line segment BC in a particular ratio, and we used that, and then we used the normal formulae for finding the distance between 2 points, and we cancelled them out until we reached an identity. We basically verified this formula, and that formula holds.